Hello. Hello, everybody. We are live. I am going to test and make sure this is all working good. Welcome back. It's been a minute since we've done one of these. Let's look at what we got here live on YouTube. There we go. It's working. Sweet. Hey, everybody. Welcome to the next stream. It's been a couple weeks since we've done one of these. Video looks a little choppy. Hopefully that gets resolved. Try this again. I don't know if people can hear. There we go. Looks like it's back. I'm going to set something here quickly. How's it going, everyone? Hopefully you all have been able to follow along with reading and even get ahead. It's been a busy couple of weeks, so we haven't done a stream in a little bit, but that changes today. If you've been following for, I work at PlanetScale. Postgres went GA 2 weeks ago. We've had a bunch of events and launch things and stuff, so I've just been very busy with all of that. But now finally got a little bit of time to get back into this and do some reading. And so we will pick up, hopefully we finish this book by the rest of the year. There's going to be a few more weeks where it's not going to work out. But try to get through the rest of this. So we will just chat a little bit, wait for people to file in, streaming on X, YouTube, LinkedIn. Hi, Kenway. I've been good. Things have been very busy. Go Monk says hello. So yeah, today, just to give you the sneak preview, the last one that we did, we ended on chapter 6, which was sharding, and that was a fun one because I do a lot of stuff with sharding in my job, right? Like one of the things that PlanetScale is known for is hosting sharded Vitesse databases. So if we go over, let me just do like so you guys can see what I'm seeing. There's, you can, of course, can watch these on watch these on Twitter, watch these on YouTube. But it, like, kind of the place to go to like look at some of the previous videos is here on YouTube. So we've got up to chapter 6 on sharding last time, and the video this time is going to be on transactions, which is like super, super important for databases. Some people may consider it a bit of a, I don't know, boring subject, but it's actually super important. And kind of one of the things that fundamentally, like one of the reasons why relational databases are so popular is because we have these things called transactions that can essentially handle a lot of the complexities of how do you deal with parallel updates and parallel reads? How do you deal with failures to write? It even helps with handling like what if underlying hardware fails, and how do we know for sure that data was written to disk and saved by our database or not saved by our database? So it's very important. We're going to dive into that today. Got a little wave. Hello there. So that's the goal. That's the plan for today. And there's, a bunch of interesting stuff. And then there's only 5 more chapters in the book, but it'll take more than 5 weeks to get through the rest of those because there's going to be a few more weeks coming up that there's too much going on. We're going to have to postpone the streams, but we'll get through it. I saw a tweet this week where someone was talking about like who would actually like books that people talk about a lot but haven't actually read. I'm sure there's plenty of people that talk about this book and don't read it, but I'm kind of glad that we're talking about it and actually reading it. A lot more fun that way, and you get to learn cool things. So yeah, so let's see. Let's look at the book and figure out where we want to start. Actually, probably the first place to start is what it talks about in the first couple of pages is the idea of acid, which is like it's a term that's thrown around a lot, and maybe some people understand it well, some people maybe don't. But let's look at, find a good place to continue drawing things over here. All right, and we'll put this up on the screen. So one of the things it talks a lot about is ACID. Oh, am I already at like the max font size? That's really tiny. Okay, let's zoom in a little bit. So this stands for, very epic little word there, atomicity, consistency. Why am I blanking on what the I is? Isolation, yes, and durability. And these are properties that people say like, hey, we want these things out of our database. Oftentimes when people talk about this, they're talking about relational databases, but really we kind of want these properties out of any database that we're using. But some of these are a little bit ill-defined, you know. So let's talk about these first before jumping into the thing that I think is really interesting about this chapter, and I think is more important to take away than understanding what ACID means, is all of the different isolation levels, because that's something that really matters when it comes to, like, depending on the kind of database that you're running and the application that you're running, making sure that you don't overwrite information that you shouldn't be, make sure that you're not getting phantom reads or phantom writes, all these kinds of things. But let's talk about this, because that's kind of like the prerequisite of just like, hey, what's the goal of our relational databases that we have? And let me just state this again. There's some people that have come in since starting. What we're doing today is we're talking about this book here, particularly chapter 7. That's where we've done a couple streams on all the chapters prior to that. We're doing chapter 7 today, which is transactions. We're going to talk about isolation levels and ACID in the context of databases. So atomicity, that's the first one here. And what this is referring to as, I mean, just like the word atomic, right? Like outside of databases, right? It has a meaning. It means like something that cannot be further subdivided, right? It's kind of down to its smallest possible subdivision. And so the idea with this is like, if we have, even if we just think about a single query, right? Maybe it's a query that, you know, is like, hey, insert 10 rows into this table. What I don't want to be able to happen in my database is I send a query to my database and say, insert 10 rows. And half of those rows get inserted into my table and then into my index. And then the other half, you know, something happens, right? Like there's a network error or the database crashes or whatever. And then now I have my database in this weird state where half of my rows that I told it to insert are in the database, but half of them didn't make it. And I just don't know. The database didn't report that to me or tell me, right? So one of the things that sounds like a simple concept, but it actually is sort of complicated to achieve given all the different failure scenarios, is we want every query, or more broadly, every transaction, which transactions can encompass multiple queries if you want them to be atomic. Either everything that query does or transaction does succeeds, all of the, particularly with writes, right? Everything that was written or modified or updated in the database, deleted, either fully succeeds or fully fails, and I can never end up in this weird in-between state where it halfway worked and halfway didn't, because that wouldn't be atomic, right? So that is, let's see, I think there's like a good example. There's a bunch of good diagrams in the book. I'm just trying to remember like what a good, yeah, that one's more like a dirty read. Let's look and see if there's there's not really a good atomicity diagram, right? But that's kind of the idea with atomicity, right? And that's really important just for keeping your database in a consistent state, because there's a number of reasons why like that could potentially fail. You could say insert these 10 rows and it inserts the first 5. And then on the 6th row, you're doing that insert. And then it realizes, oh, this 6th row, like maybe it violates one of your unique constraints, right? In relational databases, you can say, you know, I want to make sure these columns are always unique from each other. And so if it detects on the 6th row, oh, shoot, this column is malformed or it doesn't match the unique constraint, we don't want it to leave those other rows in there, right? We want it to get rid of those. So atomicity, that's something we want out of our databases, right? The second one here is one that the author of the book, and I agree with, has some gripes about this definition, is consistency. So consistency, it kind of goes into, it's related to atomicity in the sense that, right, we always want to be able to view the state of our database. Like it needs to be consistent, right? We don't want transactions that halfway completed. We don't want data that's halfway written. We need to be able to see a consistent view of the world, right? Like a database, what it's doing generally is it's modeling, it's data that's modeling something about the real world or about your users or about your application or whatever, but it's like trying to model something accurately. And you never want that to become in an inconsistent state, right? So it's very related to atomicity. But one of the things that the author points out, and I do agree with, is like consistency isn't, it's not only the job of just the relational database, right? It's not just MySQL's job or Postgres's job to make sure that everything's always consistent. It's equally the job of the engineer who's using the database, right? Because it also relies on the data that you're inserting. Like, is it actually accurate? Is it actually correct? Are you inserting partially filled in records, right? Like, so that there's a burden on, you know, the engineer who's writing the queries, who's using the ORM, whatever, however you're interfacing with your database to make sure that the data that you're giving it is good. So it's kind of a little bit silly to say like, oh, MySQL guarantees consistency or Postgres guarantees consistency, because it can't in all scenarios, right? If you give it bad data, like, then there's bad data there, right? So anyway, consistency is something that is really just as much the programmer's job as it is the database's job. But the database needs to give you tools to be able to help enforce this. One example of that are things like unique primary keys or unique constraints, right? Because as engineers, you can put constraints on a table and say like, between this column and this column and this column, there should be no duplicates, because that just doesn't make sense in how you're trying to model the world in your table. And so a lot of modern databases do stuff like that. So consistency, let's go down to the next one. And this is the one I think we're going to spend the most time talking about today, because it's what the chapter spends the most time talking about, which is isolation. And basically after, if I'm kind of recalling the chapter correctly, it's a long chapter, this one. After it goes through like the definition of what ACID is, it basically spends the rest of the chapter talking about isolation. And this has to do a lot with concurrency, because modern relational databases, Postgres, MySQL, pretty much all of them, actually there are some that are single threaded, right? But allow you to be doing multiple things at a time, right? You can be executing multiple transactions at a time. You know, if you're using MySQL or Postgres, especially if you're using a connection pooler, right? If you're using Postgres, you're using something like PG Bouncer pooled, you can have thousands of connections to a single database. And maybe there's tens or hundreds of connections directly to Postgres. And so all of those connections can be sending and requesting to do different queries or different transactions at the same time. And some of them literally are happening at the same time, right? On a multi-core CPU or whatever. So the idea is we do not want, like, we want a client, your application server or whatever, to be able to interact with the database and treat it as if there's nothing else going on, and it has the full ability to read rows and to write rows and to update rows and to delete rows without having to handle the coordination between all the other clients that might also be doing things, right? And we want to give that individual connection a consistent view of the database and the ability to read and write things without having to handle the conflicts themselves, right? Like if you've ever done actually implemented software, like parallel software that's multi-threaded or multi-process, you as the engineer have to kind of think through the different scenarios of like, what are the critical sections, and do I need a lock on when I update this variable because is it shared data or is it data that's only in my process? There's all these kind of concerns. And a relational database just wants to be able to say, you can read and write and update data, and I will handle making sure that conflicts are resolved and all of this kind of stuff. And so this gets into the lot of what the rest of the chapter talks about, which is the various isolation levels. And these are settings that a lot of different databases support. So like in MySQL, I believe there's 4, and we'll talk about some of these here. Zoom in a little bit more. Man, that does not zoom very well. So repeatable read, and this is the default isolation level. There's read committed, which is another kind of popular one to use. where is it has a serializable, right? Yeah, serializable, and then sort of the weakest form. This doesn't list them in the forms of weakest, guaranteed to strongest, but the weakest form, sort of the loosest but most performant, is read uncommitted. We'll talk about what each of those mean. And Postgres is a little bit different, but it has a very similar set of concurrency levels. And these are settings that you can set. I believe this is per like connection. You can set what transaction isolation level you want, and we'll talk more about what those mean. That's kind of the meat of this chapter. And then lastly, durability. Durability. There we go. So this is also a little bit of some of the job has to do with the database itself, like the database management system, and some of it has to do with the engineer and like how you have set up your infrastructure. Durability could be thought simply as like, do you make sure that the data that you receive gets correctly written to disk without corruption, taking into account possible hardware failure? And there's a bunch there. And this is related to transactions, but it's not really the main focus of this chapter. But then there's a bigger picture question here, which is, okay, like, sure, you could have a database that on a single server, you have a hard drive attached. The database has a perfect system for making sure that once it receives something, it writes it to a log, and then it writes it to disk. And then there's a commit that takes place, and it has checksums or whatever to make sure that there's no corruption of the data. Like, you could have sort of a perfect system to make sure it always gets written to disk. But then the question is, are you making sure that like what happens if that disk fails, right? Or what happens if there's a fire in the data center that has that server on it and it just goes away? So durability in, maybe a more modern sense, like it's kind of assumed, right? Like if you're uploading data to the cloud, or if you're saving data into a cloud database, you should have your data, every piece of data, at least doubly replicated, if not triply replicated. If not, there's some databases where every single write of a new row to that database actually gets copied 6 different places. So it depends on like how strong are your durability constraints, right? And that has to do with like, are you writing only to one data center, or are you writing to different regions across the world? There's whole different levels of thinking about durability, which would be cool to talk about more today. That wasn't really the main emphasis of the chapter, but I do actually think that's the kind of thing that I think is really interesting. Maybe we'll talk about that for a second. Zoom out a little bit. Let's go to, what were we talking about this? We talked about sharding last time, which was fun, but like that, the whole, let's see. Yeah. So like this going into durability, we kind of talked about this before when we were talking about replication. Let me make sure this fits on the screen a little better. Here we go. So a part of durability is very tied to replication, right? So if you have a primary replica type setup, especially in this is sort of an extreme example where like I have a single primary, and then I'm also making sure that every write that comes to my primary gets replicated to 2 other servers that are in my same region. But, it might be very unlikely, but it's possible that all of those databases could somehow go down at the same time if there was like a huge natural disaster. But then I also have replicas in other parts of the world, which there's a little bit more replication lag there, but at least I know I've got 5 copies of every bit of data that comes to my server, and they're spread out like geospatially as well, right? So like this, especially if you were using like synchronous replication, which is probably a bad idea if you're like replicating things across the globe, but this is like an extremely durable setup, right? Like find it very challenging to lose data if you've engineered this well, and this is the setup that you have. Let's go back over here. Okay. So I've kind of been talking a lot. There's people here. As usual, if there's anything you want to pause and talk about more, have questions on, let's do that. But if not, we'll go into talking more about isolation levels. I'm going to check and make sure that this sounds good. Last time I did a stream, there was some audio quality issues. So I'm just going to go to maybe Twitter, and let's see, make sure we're sounding good here. Yeah, there we go. Okay, looks good. All right. So yeah, let's talk about isolation levels. And what do we want to do here? Oh, this is actually, yeah, let's see, read committed, repeatable read, and serializable. But does Postgres only have 3? Maybe I'm misremembering. Oh, no, there we go. Yeah. Read uncommitted, recommitted, repeatable read, and serializable. Are those all the same names as the MySQL ones? I'm trying to remember. As repeatable read. Yeah, I think they're the same names. One of the things that the author very accurately points out is there are standard names for some of the transaction isolation levels, but people are not always consistent with what they mean by these. So read uncommitted. Again, zoom in a little bit more here. I guess I gotta do this. Close. All right. So let's look here. We've got read uncommitted, read committed, repeatable read, and serializable. And we have similar things over here. But sometimes just because the name is the same, the semantics are actually like slightly different. So what I want to do here, let's look at, we'll start by talking about, I kind of like the repeatable read. We'll start with repeatable read. So repeatable read is kind of, in my opinion, I think, is this the default? No, I don't think this is the default it is the default. Yes, in InnoDB, in MySQL. So this is a good one to start with. Repeatable read, this is one where, okay, we think about, it'd be good for me to have like an example transaction here. Actually, I think there's some good examples of this in the book. I'm going to go see, they have a good example of like you do a read and then you do a write. Yeah, okay, let's go. So that's page 244. Okay. This is a great example here. Whoa, just took me to the front page. What's going on? Man. All right, try that one more time. So here we have a transaction that begins. We do a select, and we're looking for like, we're looking for everything from our figures table where the name is robot and the game ID is this. And we do for update. This is doing something where it makes sure it takes a lock. But I'm just kind of thinking about this more generically as a transaction where we do a select, and then based on that information, maybe we do some kind of check to make sure our data is valid, and then we do an update. My camera is like very laggy right now. I don't know what is going on. I have too many. I don't know what's going on. Camera all of a sudden got extremely laggy. I don't know. We'll keep pressing on. Is it really laggy to everybody else? I'll try just to. Seems a little smoother. Okay, so many technical difficulties today. Man, it's still laggy. Can I change the settings here? This is lame. Let's try changing this. Okay. There we go. That seems better. Let's go with that. Okay. So our repeatable read, we've got, go back to our example over here. I'm going to take a screenshot of this and just bring it over into our, hold on. Bring it over in here. So we've got it in right here. Okay, so sorry. Now we're back. We're ready to go. In repeatable read, one of the things that we want to be able to do, another kind of name for this is snapshot isolation, which basically means when we begin a transaction, either explicitly through a begin, or it could just be a single query that's like a transaction on its own. What this does is for the remainder of the transaction, whether that takes 2 milliseconds or 100 milliseconds or a full second, however long it is, we're essentially getting a snapshot of what the state of the data looked like at this point in time when the transaction began. So any selects that we do, right, like data could be changing underneath us because there's other transactions that are doing things at the same time. But anything that we do as that goes, we're seeing like the snapshot from the beginning. And this, like, so the example here is maybe not the most interesting example because we do a select. So we do one read at the beginning. And when I read this here, there maybe is some amount of time that conspired between when I said begin transaction, when I did this select. But if anything changed under the hood there, we don't see that. Now, if you know anything about how Postgres stores data, I think it's kind of easier to visualize with Postgres, because the way that Postgres works is it has like a heap file for all of your table data. So let's say this is the figures table, right? We have one file that has tuples in it. Each tuple like represents the data for a row. And if anything changes, so like let's say we have this this row, or maybe this is multiple rows here, where the name is robot and game ID equals 222. For simplicity, we'll say that that's one row. If while my transaction is running, let's say that there's another transaction that decided to update some other column on this row, what Postgres actually does is it keeps multiple copies of that row on disk. So we keep that old original version that I was seeing when I first started my transaction, and it writes a brand new row. And in fact, it can have many versions of a row, because then maybe another transaction comes around and does another update to it, and it will rewrite the whole row, even if it's just, maybe it just changed values in one or two of the columns. And one of the reasons it does this is for MVCC, multi-version concurrency control, which ties into this isolation levels thing. And that's for being able to allow one transaction and another transaction that started at different times to have different views of what the world looks like. What is the reality of the data on disk? So every row that gets inserted into a Postgres database is tagged with a minimum transaction ID and a maximum transaction ID. And what that means is the minimum transaction ID is basically, this is the transaction that originally inserted this data. So assuming you're using this level of isolation, that would then translate into only transactions that have this ID or greater can see this row. And if they can't, and if you have an earlier transaction ID, and a transaction ID is just basically an incrementing counter, right? It's like an int that's always incrementing, auto increment. So if your transaction ID started before that, you have a smaller transaction ID, you can't see this row. You can only see older versions of this row. But if you have this transaction ID or newer, then you can see this row, assuming that it's committed. And then there's a max transaction ID, because rows can also get deleted or replaced by newer rows. So then you would want to know, like, if you're beyond this transaction ID, oh, this is an outdated version of the row, you should go look at the newer version of the row, right? I would love to make a diagram of that, but I feel like that would be kind of hard to draw in the limited amount of time that we have here. Yeah, I think that would be kind of difficult to draw. Well, we could try it. Let's do this here. What is going on? Let's go here. So we have make a couple of columns. We have an ID, we have a name. So this is for that figure table in the example above. We have a game ID. Let's do that. And maybe one other thing. Have a title or description. So these are the column names. And then let's say we're just going to use like one row as a really simple example. We'll use the ID that we had or the row that we had up here. So 1, the name is robot. The game ID is 222. And the description is a bot. Okay. So this is our one row that we have in the database. But what could happen, right? Like up in here, actually, I guess that's a different identifier, but you could have another transaction that comes in and actually makes a change to this. And what I'm going to add here too is these are not visible necessarily to like the database clients, right? They're just assuming that we have the transactions, that we have like all of the columns that we specified when we created our database. Actually, I'll say like TID. So we've got our max transaction ID. I'm going to spread this out a little bit more. And our min transaction ID. So these are kind of like invisible to the user. We can draw a line to kind of separate it out, right? But these are like metadata that we have on every row in our database. And so this, let's say, was the first row that was inserted into the table. So we have our, actually, I guess we don't have a maximum set yet, right? So that's question mark because nothing has replaced it yet. So far there is no transaction ID. And as long as your transaction ID when you come in, just hit my light over there, is at least 1, then you can see this, which would be all transactions. But then as time progresses, maybe, you know, a couple minutes later, we get another transaction that comes in and its ID is it, or it makes a change, right? Let's say it changes the game ID to be 100 and it changes the description to new bot, right? The name is still robot. But what it tried to do is it changed the row that had ID 1 to this. And so conceptually, like the way you as a programmer would think about it is like, oh, this row just got, like we could just delete this and 2 of the column values got replaced. But internally, what's actually happening in Postgres is this row sticks around, this row gets created, and maybe the transaction ID for the row that made, or for the transaction that made this update, you know, this is a little ways down the road. This is a few minutes later. So maybe its transaction ID is like 100, or maybe it's 1,000, whatever. So then over here, the max transaction ID, we would set this to 100. So any transaction, if there's still any running whose transaction IDs are less than 100, they can still see this version of the row. But for the current transaction and any future ones, they're going to see this version of the row. And then again, this can continue to happen, right? So we might have then a minute later, another transaction comes in and changes this to, you know, a different name, right? Let's say, and leaves all the other stuff the same. And maybe this transaction had an ID of 200, right? And so now the max here is 200, and it goes on and on like this. Sorry, you can't see that other column very well. There we go. It's a little better. Okay. So and this is a good question here from Juan. How do unused rows get cleaned up? That's a great point. We'll talk about that soon. But this is basically what Postgres is doing when you update existing rows, right? It actually makes a new copy and it keeps this metadata internally of which transaction was the one that made this change. On the previous one, what's the maximum transaction ID that can see this? I might be getting some of the details slightly off here, but it's generally the concepts that matter at this point, right? So this is what facilitates that functionality, because you might think like, if I have a lot of different transactions happening and one of them starts, and then while that one's running, another transaction changes one of the rows that another transaction needs, like that can be kind of complicated. So you have to have some system to be able to keep track of potentially multiple versions of a row at any given point in time, right? And then, yes, this is another good question, which is also related. So do min and max transaction IDs get reset at some point? Yes, well, kind of. This is in Postgres. Again, different databases do this differently. There's a process called vacuuming, which helps clean up some of these unused rows and helps with a transaction ID wraparound if you run out of transaction IDs. But to I guess one sort of note here, and this is actually especially true of MySQL, which handles it a little bit differently. This is one of the reasons of many why you don't want to have long-running transactions, particularly in an OLTP style database like MySQL, like Postgres, like SQLite. And partly it's because if you have some transactions that run for a really long time, then that means you need to keep around more old versions of rows that might only be being used by one transaction that, is some super long, hour-long query that you ran that's doing some complicated analytics or something, while every other query in your database has moved on. But we have to keep around a bunch of old versions of rows just because this one really long-running query needs a snapshot of what the database looked like an hour ago because it's running for a really long time, right? So let's talk briefly about what MySQL does here, and then we'll address some of these questions. Actually, let's address the questions first since you guys asked them. So how do unused rows get cleaned up? Well, in Postgres, there's sort of multiple phases here and multiple ways that you can do it. There's a process called auto vacuum, which can also be manually executed by just typing the command vacuum. And what it does is it will go through and let's say, we have several versions of things and we've detected like, okay, there's no current running transaction that's older than 100. Maybe the oldest current running transaction has an ID of 150, something like that. So it will go through when you call a vacuum and it will scan all of your tables and look at and find, okay, I see that this version of robot from way over here has a max transaction ID of 100. All of my transactions have now surpassed that. They're all passed. No transactions need to see this old version anymore. So I'm going to mark this as reusable space. So I'll just indicate that by making it red. It doesn't actually like recompact the table. It basically just says, hey, I've identified that we don't need this anymore. It's excessive to keep this around. So I'm going to say this is reusable space. And so now that slot can be reused as long as something can fit in there. If I insert another row or make another row modification later, I can go reuse this spot. So let's say there was yet another version of this row. And again, it could also be used for inserting new rows, but we're just kind of like looking at one particular row and all of the versions of it here. Let's say I change the description again to bananas. And the transaction ID for this is 300. So when this came in, I added like a whole new slot in the table. But what I could have also done is since this was marked as reusable space, I could just overwrite that version and then put it here. So that way we can start to reclaim the space instead of just having these gaps all over in our database, right? So there's that level, and then there's a more extreme level, which is there is a command, I believe it's vacuum full in Postgres, which not only does the marking things as reclaimable, but a vacuum full actually will rebuild your table. And essentially, if over time, your table can end up with a bunch of these little gaps that may or may not get reused, and it will sort of recompact your table and actually reclaim the disk space. But that process can take a long time for really big tables. So it's something that And I believe, if I recall correctly, it takes like a full table lock, so you can't really do much with the table during that time. So like there's this trade-off there. And so yeah, when we do these vacuum operations, it can go through tables and to this question of do min and max transaction IDs get reset, it can figure out like, okay, there's nothing older than whatever the current transaction ID, so let's clean up everything that's older than that age. And the other thing about Postgres that can happen in sort of extreme circumstances, there's a background worker called the auto vacuum, which essentially does this vacuum automatically. It sort of automatically every so often, which is specifiable, it will scan through tables and look for these sort of dead rows. But if you have a database that is writing a ton of data to the table, it can actually get into a point where your auto vacuum process can't keep up with how fast you're writing new data. And so even though you're attempting to reclaim space, your auto vacuumer can't keep up with just a massive amount of writes. So you have to basically in Postgres, you have to pay a lot more attention to things like, this is called table bloat, when you have like many versions of rows and some of them aren't even needed anymore, but the space isn't getting reused. You have to pay a lot of attention to that in something like Postgres. And MySQL, a little bit less so. Maybe we'll touch on that briefly. Someone asks, are you following the first or second edition? And the answer is, this is the first edition. So the second edition, it would have been cool to do the second edition, but I think there is like a preview access that you can get online, but it's not actually officially out yet. It doesn't officially release until like the spring of next year, I think. So I wanted to just do this. I ordered it like a couple months ago. And so we're just doing edition number 1. I think it came out in 2017. So it is a little bit dated. That's not that old in terms of book years, but with database technology changes, new things come out, all of that. So I'm sure the second edition will have some nice updates, talk about some things that have changed in the past 8 years in databases. And there's definitely been some changes. So a LinkedIn user asks where to ask questions. You found it. I think on LinkedIn, it's kind of odd. It's like literally just shows up as like a comment below the video. You can also go to the YouTube channel. Let me share a link to it. Although I don't know if you'll see this on LinkedIn, but you can go here, youtube.com/BenJDicken, and you can watch the live stream there. And there's like a live comment box, similar on X. Okay. Good questions. Good questions. Would all replicas have to deal with this individually? Oh, that's a good question. Off the top of my head, I'm actually not sure in Postgres's case exactly what happens here. I would assume that as long as the replicas are replicating over the log, that they're just going to tail the log and follow what the primary does without having to run their own separate vacuum processes. But I'm actually not sure. I have never specifically thought of that question or had to answer that question myself. That's a good one. Yeah, I think there are a fair few chapters still not on O'Reilly. Oh, okay. So yeah, I haven't looked super closely. So maybe the preview of the second edition doesn't have all of the chapters. So for now, this is your best bet. The book is like $40. So I could understand if you don't want to buy this edition and just want to wait till next year for the new edition. But then sometimes I also think life is only so long. There's only so many hours in the day. So I'm just going to read what exists now, even if it is slightly out of date, but still very valuable. Okay, let's go back to presenting. Let's talk briefly about what MySQL does here. MySQL does something different where it does not create a whole new version of the row every time there is an update. What it does is it actually does the update in place like we talked about earlier. Let me make a copy of this whole thing. Let's paste it over here. What? Whoa, 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 whoa. I don't know what is happening. Okay. So in MySQL land, we do not need to make lots of versions of rows. And this is arguably an advantage of MySQL because basically in MySQL, there still can be table bloat, right? So table data is actually stored directly in B trees if you're using InnoDB, which a lot of people are in MySQL. So you can still get bloat in your B trees, but there's sort of a cap on how much bloat you can get, right? In Postgres, you can potentially have like a table where the on disk storage size says it's consuming, 100 gigabytes of your disk, but there's actually only, 30 gigabytes of real table data in there, and the rest is just bloat, right? That kind of stuff tends to not get that extreme in MySQL. So in MySQL, if you need to update something, right? So we had like our original version of this row. Oh wait, where did our original version go? Oh, we deleted it. Okay, so I'm just going to make this be the original version. Pretend that's the original version that we had earlier. Instead of creating all of these different versions, each time that we want to make this change, we would just say, okay, this is the original version. Now I want to change, to change the name to monkey. I'm just going to overwrite the existing row with, whatever column is changed, right? And then again, I later want to change the description to bananas. Don't need all this anymore. I just change that row to have the description of bananas. Now, we still need some way of knowing what the old row values were, because in MySQL, just like in Postgres, we have this repeatable read isolation level, right? Where we essentially want to be able to, we want to be able to essentially have this snapshot type semantics where when my transaction begins, all of the reads that I do are based on what the database looked like when that first started, and things could change while my transaction is running. So MySQL has a separate thing that it calls the undo log, where every time it makes a change, so let's see, what did we change at first? We changed the name to monkey, and we changed this to bananas. So I'm going to make a little box down here, and I'll call this, I don't know why the colors are like that. Make it blue. Call this the undo log. So this is just a special place reserved on disk for information about how to undo changes that have already happened. Get rid of this comment here. So what we would do is as those updates took place, right? So we know at one point, transaction ID, let me get rid of these too. Let's just get rid of all these. The transaction ID, I think with 200, change the name to monkey. So we would basically just add a record. So transaction ID 200, ID equals 1, name change to monkey. All right, this isn't literally the actual format. I'm just making something up. We store a record of hey, previously the transaction with ID number 200 for row ID number 1 changed the name to monkey. So if I ever need to go back and transaction with ID 150 needs to see what did the row look like when my transaction first started, it would look in the log and it would say oh, transaction ID 200 changed the name. I guess we would want to keep the old version. What was it? It was robot to monkey. So it would go, okay, I see that it was changed to monkey later on. So I'm going to actually use robot. And then, there was also, I think we had transaction ID 300 changed the description from a robot to bananas, right? And so we're essentially keeping records of all of the changes that have been made. So we can keep our tables a little bit more compact by actually making the changes in place, but we need to maintain this separate log data structure. And then also this log data structure needs to be able to be cleaned up, right? So as transactions complete and we sort of progress forward in time with our transaction IDs, we can eventually reach points where it's okay, we can get rid of everything in the undo log that's older than transaction ID 200 and older, right? So we can clean up old rows, new rows get added to our undo log, but then we clean up old rows. But this is another point in, if you have really long running transactions, then your undo log can actually become many gigabytes, because if a lot is changing and you have transactions that are running for an hour, we need to store a lot of undo history, and then that hampers the performance of those queries. So it's a trade-off, right? We have this extra data structure that we have to maintain. Performance-wise, arguably, could be better, could be worse in some situations, but it's nice because we avoid a lot of the table bloating and vacuuming issues of Postgres. So in Postgres, does the vacuum process mark pages as deleted, or does it handle fragmentation in a way that makes them reusable? So in Postgres, the regular like auto vacuum process only just marks things as like, hey, this space is reusable. That was indicated by like me putting 100 over here, right? But it's the, like if you run a vacuum full, that's when it actually does table recompaction. But then when you mark spaces usable by auto vacuum, that means future inserts or updates could potentially reuse those empty slots as long as they can fit in there, which isn't a guarantee, but if they're, the same size or less, they can reuse those spaces. Is there also something like vacuuming for the logs in MySQL? Yeah, I don't know. Probably, I'm sure there are more people more experienced in MySQL who would know if there's like commands that you can run to manually do undo log cleanup and stuff like that, but I'm not sure off the top of my head. It's a very good question though. Man, we spent a lot of time talking about this, which I love it, but we hardly actually, I guess this kind of was all for talking about isolation levels. So this was all motivated by, okay, if a database is saying, I'm going to give every transaction a snapshot, and for the entirety of that transaction, whether it takes a millisecond or 10 seconds or 100 seconds, you're going to get a consistent view of the database at that point in time. This is how these databases handle that. MySQL does it a little bit differently than Postgres. And this is one of those things where like Postgres is very popular right now, which is great, right? Lots of people like using Postgres. It's awesome. In many ways, it's a very cool database. But there are some people who get this perspective of like, oh, Postgres is popular. Lots of people are using Postgres and choosing Postgres. Therefore, it must just be better than MySQL, right? And then people get this idea that, MySQL is just the old crusty database that used to be used a decade ago and nobody wants to use it anymore today. There are definitely things that could be better about MySQL, especially when it comes to the licensing and all of this kind of stuff. But there are some places where MySQL is arguably better than Postgres. And this is an example of, it sort of depends, right? Maybe for some people, the whole table bloat and vacuuming issue isn't that big of a deal. Like, for example, if you have a database that isn't very write heavy and is mostly read heavy, and if you have a database where you can, you have like peak hours where there's a lot of traffic, but you have very distinct times where, hey, there's not much traffic on the database. And during those times, we can do space reclamation or use a plugin like PG Squeeze to rebuild tables. Great. But for some people, this whole thing of like making many versions of rows and having to vacuum, this is actually like a huge problem for some companies. Again, especially if you have like a lot of writes and you do a lot of overwriting existing rows or writing new rows and expiring, deleting old rows, like this architecture can actually be like a really big problem. And for those kind of companies, this is actually way better. So say what you will about, it's actually not an older database. I think technically Postgres is older than MySQL, but say what you will about, oh, it doesn't have as good of a plugin ecosystem, or it's not as popular, or there's not as many companies that host Postgres databases. MySQL is really good for a lot of things, right? Yeah, so someone asks which performs better. I don't have good benchmarks to give you off the top of my head, right? Like ultimately what it comes down to is we want to see this in real world scenarios. So there's a lot of it depends on like how long are the running transactions, how frequently are there writes and updates versus reads. Like there's a lot of it depends here. This can actually be very good for writes, even though it does produce a lot of like writes. It can be nice because instead of having to try to update existing entries in a B tree and then add something to a log, it's just boom, new row, new row, new row. So it's a very simple model for just every update just becomes insert something new into the table. So that can be good for performance. But then again, like there's some instances where, especially once you take into account all the work it takes to maintain that database, this is better for a lot of people. Yeah. All right. So we have a few more minutes. What else should we talk about? There's a few other isolation levels. and I'll get this table up above my head here. So we were talking mostly about this one, repeatable read. There's weaker ones, which basically, and the trade-off with all of these is essentially like what kinds of isolation guarantees, like how isolated is my process from everything else, all the other transactions that are running, versus performance. Because the more isolated you are, there's generally a hit on performance. That's just kind of the trade-off. So serializable is the most extreme, which basically means all transactions, even if there's lots of simultaneous connections and lots of things going on simultaneously, will be perfectly serializable in the sense that we could put an exact order, even things that were happening simultaneously. Every transaction looks like it happened one after the other. But this requires a lot more locking on tables and indexes, and some queries will have to wait on other queries. Sometimes you can even get into deadlock, where you have transaction A waiting for B to release a lock, but then B is also waiting for A to release a lock. And so now one of those transactions just has to get killed for the other one to progress. So it hits performance when you're in serializable mode, and MySQL has, all the way down at the bottom, a similar mode, all the way up to read uncommitted, which is like very loose, which this literally means like I can start a transaction and I can start reading data. And if there's another transaction that is making writes underneath me to the same data that I'm working on, I can actually see all of those writes taking place. So I could, in one transaction, I could like read, we go back to, I could say, hey, give me, the row with ID 1. Oh, its name is monkey and its game ID is 100. And then while my transaction's running, we overwrite this with, we've changed the name to elephant. And then if later in the transaction, I try to read that same row again with a select, I will see elephant. So literally data can change underneath me. So that's really not isolation, right? I'm not isolated from what other transactions are doing. I can literally see all of the writes that the other transactions are doing. But the nice thing is, from a performance perspective, if I'm doing this, I don't have to handle locking rows and saying, I'm writing this row right now, nobody else can look at it, all of these kind of things, right? So basically all the queries can just zoom as fast as they can, but you can end up in weird states where you have an inconsistent view. You basically break your acid, your consistency, when you start to play loose with things like that. Yeah. So we're almost at 10 o'clock. And I am going to go at that time. But any other questions or anything? In what real cases read uncommitted can be useful? I'd probably just not use it. There's a reason why it's not the default. Yeah, I mean, I guess there could be circumstances where you don't actually care about, like, if you don't actually care about precision, you just want estimates. So like if you're doing financial transaction processing, you'd probably never use that, right? If you're doing anything where like everything needs to be consistent, the balances need to be consistent, the payments need to be consistent, you'd never use that. If you're doing something like, I don't know, or things where you're counting statistics and those statistics don't have to be super accurate, you're just getting rough ideas for view counts or page visits or all this kind of stuff. Maybe there's cases where for the sake of performance, you'd do something like that. But even then, you'd probably just be better off having better guarantees like read committed, and then engineering your database to work better around those things. What is the default? Oh, great presentation. Thank you. What is the default isolation level for Postgres? I believe it's repeatable read, or read committed is default. And then I believe here it is, yes, repeatable read for MySQL. Yeah. Cool. Well, thank you everybody for watching today. A few technical difficulties, but we made it through. And I do plan on doing one next week. So next week is chapter 8, where we start to talk a little bit more about transactions in a distributed environment. It's called The Trouble with Distributed Systems. So that's what we'll talk about next week. If you want to read along, and I will talk to you then.